Alright, we are done with Karnaugh Maps, and we have been able to show you how we can put gates together to come up with some good functions. Okay, maybe a BCD divisor, maybe a BCD or a 2-bit adder or something like that. We've been able to show you that. And then we have shown you the Karnaugh Maps and all of that. The problem is we started with transistors. We said, well, we can put two transistors together like this to build a gate. Okay, that's an inverter. Then we can put four transistors together like this to build an AND gate. Okay. Then we said, well, now let's use Karnaugh Maps to put these gates together. For example, we said, well, this is a Karnaugh map that let's say A1, A0, B1, B0, A and B are being 2-bit numbers, and we want to find a comparator that generates a 1 when A is greater than B, considered that A is a 2-bit number, B is a 2-bit number. Okay, 0, 0, 0, 1, 1, 1, 1, 0. Let's just fill this 0, 0, 0, 1, 1, 1, 1, 0. A is greater than B. This is A is greater than B. This is A is greater than B. This is A is greater than B. A is greater than B. And then 0 everywhere else. Okay. And then we say, well, see, A greater than B, that means if A is 1, 0, B is 0, 0, there is a 1 here. If A is 1, 0, B is 0, 1, that means A is 2 and B is 1, so A is greater than B, and so on. And to build this, I generate this as a map, this as a map, this as a map, and then my G output becomes A1 B1 bar, right? A1 B1 bar, ORed with A0 right, B1 bar, B0 bar, ORed with third one is A1 A0. I'm talking about this map here, A1 A0 B0 bar. Okay, so nice. I was able to build a comparator that has a 2-bit input for A, a 2-bit input for B, and then it has a G output. Okay. What I like to look at it now is, or what I like to look at right now is, it was good to go from transistors to gates. That was easy. It was easy to go from gates to these comparators and other components. But then when I have a larger design, I cannot always go back down to gates. I cannot always go back down to transistors. When I have a larger design, I like to think of it this way. For example, I like to think of it as here is an 8-bit input A, here is an 8-bit input B, and if, for example, A is greater than B, so I need a comparator to compare A is greater than B. If A is greater than B, I want to add A with something else. If I want to add B with the, or for example, if situations change, I want to add, for example, if A is greater than B, I want to add them together. If A is less than B, maybe I want to subtract them or something. I want to think at a higher level. And so this is sum. So instead of needing gates, I need upper level components. I need comparators. I need adders. I need perhaps multipliers. I need upper level components. So I started with transistors. I put gates together. Now I like to put more functional units together. Okay. The problem is, can I use Karnaugh Maps? Perhaps not, because for this simple comparator, for a 4-bit comparator with 2-bit inputs, I can use Karnaugh Maps. But then, if the comparator becomes a 4-bit comparator, what do I do then? Okay, and this is what I want to be looking at next. All right. We have shown gates, we have shown components, and let's say that someone has asked you to build a circuit that creates the absolute value of the input and the output. Okay, you say, well, the input is W, 8 bits, the output 8 bits. Okay, I want the absolute value of the input to go on the output. How do I do this? Go with Karnaugh Maps? No. What you do is you say, well, I have adders, subtractors, multiplexers, comparators, this and that, and now I'm going to build this circuit using these upper level components. Okay, this is how you go about it. You look at your input, you say, well, my input is an 8-bit input and it's 2's complement input. If bit number 7 is a 0, I'm going to send it through because it's a positive number. So you say, you take bit number 7, put it into a multiplexer. If it's 0, okay? If this is a 0, okay? Your W is positive. And then you're going to send your positive number all the way through to this. Becomes the absolute value, or the positive number that becomes the output. On the other hand, if your sign bit is a 1, is a negative number, then you complement all the other bits. Okay, you complement all the other bits and add a 1 to it, carrying a 1. Okay, if it's a 1, means your number is negative. Your number comes through here, gets complemented. Then you have a 1 here for carrying, adding a 1 to it, and then passes through from here, appears on the output. So this circuit produces the absolute value of your circuit. Okay, let's do another example here. What if I ask you to have a circuit with A input, B input, 8 bits both, build a circuit that puts the maximum of the A and B on the output. Okay, how do you go about it? Well, you take a comparator, AB. If this is 1, A is greater than B, and therefore take a multiplexer, 2 to 1, 8-bit multiplexer. Okay, if this is 1, you want A to go to the output. Usually this is 0, this is 1, therefore you complement this. This becomes a max finder. Okay, so this is how you will do your design. You will think at the upper level. You put these upper level components together, and these upper level components become the elements of your designs. Later on, these maximum finders, these absolute value circuits, these become the circuits that these are the circuits that you will be using for upper level design. Okay, we are done with the combination circuits, and next we will be doing storage elements. Okay, thank you.